Hello. Good evening, everyone. Am I audible?
Yes, ma'am.
Okay, let's wait for 2-3 minutes for others to join, then we'll start. Okay, so I think enough people have joined. Uh, can you all please check if the problems are visible to you? Week 5, see under live coding, there should be 3 problems. Are they visible?
Yes, ma'am.
Okay, okay, let me
Ma'am,
share my screen.
ma'am, I just wanted to confirm week 6 will be taught after next week,
After
ma'am.
after quiz 1 is done. Yeah.
Okay, ma'am. And next week we'll be doing revision, right, ma'am?
Yeah, next week there will be no live coding, only revision sessions.
Got it, ma'am. Thank you.
Ma'am, week 6 is only a revision or syllabus?
Week 6 after quiz 1.
Oh, okay.
Okay. Can you see my screen? Visible?
Yes, ma'am.
Okay. Alright, so everyone go to the first problem. So this is saying an airline company wants to make airport to connect n cities level 0 to n minus 1 all across the country. Right. So we have to write a function called airport which will take distance map as an argument that accepts a weighted adjacency list. This distance map is a weighted adjacency list in the following format. So this is the format of the list. So distance map is basically it is a dictionary inside which each of the keys are what? Source index. That means basically all the cities, right? So every city has an index labeled from 0 to n minus 1. So for every city, corresponding value will be what? A list of tuples. So inside every tuple, like if I say the first source index is 0, okay. Now from 0, let's say I can travel to city 1 with a distance of 1000 kilometers between them. So for source index 0 inside the list, in the first tuple there will be destination index 1, comma 1000. So basically every entry in this dictionary is what? For every index or every city, we make that city as the source city. So from that source city, what all cities can I go to? by covering what distance. But this adjacency list, this thing you have to prepare. Okay, this dictionary format you have to prepare. So we are not going to take the input in this format, right? But what is the point of this function? That it should return the minimum distance of airport to connect all n cities. That means I want to connect every city with a minimum distance. So this is nothing but a spanning tree, minimum spanning tree problem, right? So we will attempt to solve this using Kruskal's. Now, first you see this is the sample input, right? So we have 7, that is the number of vertices or number of cities in this case, and then we'll take a list like this as input, a list of tuples. Now inside this list, what does every element mean? See the first element 0, 1, 10. That means source index is 0, destination index is 1, distance between them is 10. Again, source is 0, destination is 2, distance between them is 50. Right. So when I convert it into this distance map, it should look like source index will be 0. Corresponding to that, the value will be inside this list 1, 10, 2, 50, whatever distances are there, right, to the destinations for 0 source. So like this, for every node, we'll create an entry for source 0, for source 1, for source 2, 3, 4, like this. Okay. So this is the code that is given. This is the input. We are taking the size, which is the number of vertices or number of cities, and edges. So this list is called edges because these are all edges only, right? From one city to another city, if I'm going, that is an edge between two cities. Now after that is taken as input. Okay, so here it is done only, you don't have to do it. So they have given it in the prefix code. So the WL is an empty dictionary in which basically we are forming this distance map dictionary, right? So see, for I in range size, that means for every city we will create an entry in the W list. Initially, for every key there will be an empty list in the value part, right? Then we have to populate the values also. So initially in W list, keys are what? Every distinct city, and corresponding to that there are empty lists initialized. Now to populate the lists, you will check. So for ed in edges, that means the list that you have taken as input, in that for every tuple you are going to check what is the 0th entry, right? WL ed 0. So the 0th entry in the tuple is, for example, take the first tuple 0, right? The 0, 1, 10. So 0th entry is 0. Dot append what? In W list, against the 0th index we will append ed1 and ed2. That is the second and third entries, that is 1 and 10. So destination index and distance. So ultimately this, after I complete doing this for all, right, what will I get? This distance map. Understood? Now see, I have to find out the minimum spanning tree or the minimum distance that connects all n cities. But I have been asked to write a function called airport. So first let's define that function. So define airport.
Uh,
Sorry?
it should return a integer minimum distance means.
It should return the minimum distance that should be taken to cover every city in the airport network. Okay.
Sorry to ask,
Yeah.
can you explain the 11th and 12th line, please?
Yes. See, first in the W list, what is happening? For every city, I am creating a key, right? And corresponding to that, the value is an empty list. This
Yes,
line 9.
yes.
Now in edges, this list that I've taken as input, what is present? A tuple in which there are 3 entries, right? Every element is of this format. So in this tuple, there are 2 nodes, 0, 1. These are 2 cities, and the third entry is the distance between them. So we have to form this distance map, that for every source index, what all destination indices are there. That means, let's say my source index is 0. From 0, starting from 0, what all cities can I reach, right? And what is the distance between them? So for ed in edges, this will pick the first tuple. For first iteration, let's pick the first tuple 0, 1, 10. Okay, what are we appending in W list? So in W list, ED0. ED0 is what? Which index? 0th index.
Yeah, first one.
Okay. For that, I'm appending this tuple ED1 comma ED2. So ED1 and 2 is what? 1 and 10 from this tuple. That means for source 0, I can reach destination 1 by covering a distance of 10. Similarly, we'll
Why only 0 and 1?
no, not only 0 and 1, whatever is present. Okay, for every tuple we are checking, right? For ED in edges. So you will be traversing through all the tuples in edges. It is a dictionary we are creating. So wherever we find 0, it will add to that 0th entry. Okay, similarly for 1 also, 2 also, for every edge, for every vertex. Okay, so that is the distance map creation. Now this distance map will be used in this airport function. So this takes distance map. Now what is the first thing I should do? My thought process should be that I need to find what all edges are going to be there in my minimum spanning tree which covers all n cities, right? For that I thought that I would be using Kruskal's algorithm. So I have to call that algorithm first. In airport function, first thing I have to do is call that Kruskal algorithm to find out what is that list of edges that will be present in the minimum spanning tree. So before I can write the definition of this, I have to define what is the Kruskal algorithm. Okay, then I can write the rest of this. So Kruskal algorithm, what is the way it works is that it finds a minimum cost edge, right? It is a greedy algorithm. So at every step, it will find the optimal solution. The minimum cost edge I have to start from. So let's define Kruskal. So this Kruskal algorithm, what will it take as its this thing?
Distance map.
Is it called distance map?
It's the distance list.
So I can call it like this, right? I can write W list. It will take this W list. Same thing, W list distance map are same thing. Okay, I'm writing this because here when I call that algo, so I will write it like this. R, let's say inside R variable, I want to store whatever Kruskal returns. So Kruskal, then you write the argument as distance map. Okay, but in the definition of Kruskal, I'm mentioning as W list because that's what we did here in the prefix code, right? So what is this going to do? First, we have to create three things. One is an edges list, another is a component dictionary, and the last one is the list which will contain the edges that are there in the final minimum spanning tree. So we have to return that list. Okay, first let's find out what all we have to initialize. First let's take edges, then component. I'm initializing all together. Then let's call it TE. These are the edges. Now you have to initialize them as first one, edges is a list. Second, components is a dictionary. And the last one is also obviously a list. Now we'll see where we need these. Okay. First thing we have to do is for u in wlist.keys. That is we have to now traverse through this w list that we have created. Okay. This distance map, w list, whatever it is, let's traverse through it. So for u in wlist.keys. So if there are 7 keys, this loop will revolve 7 times. Okay. Now what am I doing inside the loop? For every key, that is for every city. This edges list that I have initialized, inside this now I'll populate it. So edges dot extend. Okay. Edges dot extend. First let me write, I will then explain. D comma U comma V
Ma'am, W list also works, no? For U
Yeah,
in
yeah.
W list alone. Just dot keys is like
Yeah, you
that
can
also
use
works.
that also. Fine. Okay. For so this is the format we want now. D comma U comma V. Okay. So D comma U comma V for so this is not present, right? Where am I getting this from? For V comma D in W list itself. W list of U. So that's the format in which it is stored in W list. In W list for every city, the corresponding value present is a list of these tuples V comma D. This format, destination, distance, right? So for every U, now in the edges list, what we are storing for every U, we are going to store this tuple D comma U comma V. So let's say from this one, take this example. This is the first tuple. So in W list, this 0, 1, 10 is stored like this. For source index 0, the corresponding list contains a tuple which contains 1 comma 10. So destination comma distance. So now I'll pick these three U, V, D and put them in a tuple like this D comma U comma V. So it is 10 comma 0 comma 1.
Ma'am, why not U comma V comma D?
We'll see what I'm doing. Okay. We'll see after this why this is needed. So D comma U comma V in this format I'm adding. Now this I will do for every U, right? So what is this basically? These are edges U and V. Every one of these distinct D comma U comma V. These are representing every edge in the graph, right?
Oh, yes, ma'am.
So these are unique edges that I am finding for every source destination. That means every unique edge will be present in this edges list. Okay, this is just to create all the edges and put them inside a single list called edges. Okay, now after this, in Cruskal first I have to do what? I have to start from the smallest weight.
Ma'am,
Right?
this is already present, no? What we created is just swapping of probably that
Yeah,
change the
so that I
position of.
can sort. Right, that's why I
Okay,
did.
okay.
So
But
I will
otherwise, this is
drag.
nothing but the original W alone, W list only, right?
Right. It is not the W list. The W list is a dictionary, right? Edges is a list. So it is similar to the input that we took.
Ah, input, correct.
Okay,
Input.
that's same edges. Now in this, I did this. I took the distance in the front so that I can sort according to the distance. Okay, because I need the minimum distance first. But before I do that, there is one more thing. Let's initialize this component. Okay. So I will write component of U. So for every U, the component U will be assigned the value U itself. That means for every vertex, the component in the component dictionary, the keys are what? Every vertex. And initially, their values will be the same vertex only. That is, each vertex is in its own component. Okay. So why we need component first of all? Cruskal, does it work for cycles? Can I have cycles in the minimum spanning tree?
No.
No, right. So I have to get rid of all such edges which are creating cycles. So to find such an edge that will create a cycle if I add it to the MST. So the idea is that, let's say you have, take this graph for example. So here you can see from 0 to 1 there is an edge, from 0 to 2 there is an edge. Okay. Let's say in the spanning tree I have taken these two edges. Okay. Just for example, if I have taken 0 to 1 this edge and 0 to 2 this edge, so can I say that 0, 1 and 2 are all in the same component?
Yes.
Right?
Yes.
That means I have to keep on updating the component. Since initially I'm saying that 0 is a separate component, all vertex are separate components. So I have to update every time I add an edge, I have to update the component that now these two vertices are in the same component. Now after I added these two edges 0 to 1 and 0 to 2, if I try to add this edge 1 to 2, so this will create a cycle, right? So how can I detect that? So the current U and V are what? 1 and 2. These are the two U and V I want to connect using an edge. So I will check whether these two are in the same component or not, right? Only if they're in different components, then only I can add an edge. If they're already in the same component, then if you add the edge, it will form a cycle. So that's why we have defined this component dictionary to keep track of the components, like which vertex is in which component. Okay. So initially, since I have added no edges, all the components are different. Now all initializations are done. After this, I'll come out of the loop and I will sort the edges list. Okay. So once I sort it, I will definitely get the smallest edge in the beginning, right? Because it is sorting according to the distance, definitely. First item. So we have to start from that, the shortest distance. Now the actual Kruskal logic, let's write it. So for D, U, V, for each such tuple in edges list, first we have to check whether U and V are in the same component or not, because if they're in the same component, I just said it will form a cycle if you add the edge, right? So first you will check if component of U is not equal to component of V. Up to this, it is fine for everyone?
Yes, ma'am.
Okay. Now, after you check this, if it is valid, they are in different components, then we can try adding the edge. So where am I adding the edges for my minimum spanning tree? In the TE list, right? So TE dot append. What will I append? U, V. This is the edge I'm adding. Okay. Now in this variable, let's take a variable C. In this, let me assign the component of U. So think of this as the first iteration. At this point, component of U contains what value?
U.
U only, right? So U is stored, whatever U is, that is stored in C now. Okay. Now next thing, we have to update the component since we have now added an edge. So for W in W list dot is, and check if wherever you find a match. Okay. So if component W is equal to C. If you find a match, you will update. So update to what? Now component of U will be updated to what?
It's adjacent.
We can update it to component of V because they are both now in the same component. So I can write component of W or whatever, the current U, same thing, is assigned the same component as component of V. So let's say for this edge, okay, 0 and 1. So initially 0 was in 0 component, 1 was in 1 component, right? So this line 8 condition satisfied. So we appended this edge 0, 1 in TE. So this edge will be there in our MST. Next, I took in C, I took the component of U. So U was 0. So C contains 0 now. Now you're going through all the keys in the W list. Wherever you find a match for 0, right? The component of 0 is going to be 0, right? So that match will be found in line 12. So now the component of 0 is updated to what? Component of 1. So component of 1 was carrying what value? 1. So now component of 0 will also show the value 1. That is component 0 and component 1 are now both in the same component. So the value is 1 for both. Okay. So we are updating according to the destination vertex. But both should be in the same components. That's the point. Okay. Now like this, if I continue taking all the edges from the edges list and do the same procedure, then wherever there is a chance of a cycle happening, right? Let's say in the same way I have added the 0 and 2. Okay. So initially 0 is in which component now? After this, if I am checking, let's say for this 0, 2 edge.
2.
So 0, component of 0 will now have what value stored in it?
1.
1.
Didn't get, ma'am. Can you please repeat once?
So I said that the previous one, think of it as the first iteration. So I was adding, let's say, this edge 0 and 1, right?
Yes.
So then the component of u was updated, that is component of 0 was updated to the value 1, right? So
Yes.
that both are in the same component.
Yes.
Now next, if I want to add this edge 0 and 2, then I am going to again check what is the component of u. So component of 0 right now is 1
Yes.
and component of 2 right now is 2 only as
Yes.
initialized. So both are in different components, so I will add the edge. Okay.
Okay.
Again do the same thing. Then component of u will again be updated, right? Updated to what?
2.
2. Now, if I try to see, wherever this C value matches, in all such places I have to update. So another component is there whose value is 1. Which is that? Which is what? Where is the component value 1? Except for 0th node, the 1 node also has component value as 1, right? So there also we'll find a match, this match. See, after the first iteration, component 0, component 1, both are containing the value 1. Up to this, clear?
Ma'am, but we have already updated this value in the previous iteration.
Yeah, you have. I'm coming to that. But this is clear, right? Both component 0 and 1 are having the value 1 right now.
Ma'am,
Yeah.
this U and V will be different, right? So,
Yes. So the W value will change because it is inside a for loop, right? So we are going
yeah,
through every W values.
yeah. So the components will also be different for so is
Initially
yeah,
they are going to be different. Now after I added this at 0 and 1, now both nodes 0 and 1 are in the same component, right? Both are having the value 1 stored in it. After the first iteration. Is this much clear?
Yes, ma'am.
Now when I'm trying to add this at 0 and 2, then also I will run the same for loop, right? For every W in W list keys. That is, I'm going through every vertex and checking the component. So how many vertex are there which have the component 1 right now?
2 vertex.
0 and 1. So both will be updated with current V component, that is 2. Right?
Yes.
Because how many times will you find this match? 2 times. C value will be 1. So component W is equal to C will be true for both node 0 and node 1. So both nodes will be changed to the value 2. So now how many nodes are in the graph after this update which have the same component? 2.
Ma'am, I'm getting confused, ma'am. Ma'am, when we add 2,
Hmm.
then we are adding it with respect to which edge?
I am saying this edge 0 and 2.
Okay.
Okay. So after this update is done, all three of these 0, 1, 2, all three nodes have component value what?
2.
2. That means they are all three of them are now in the same component. Next, if I try to add this edge 1 and 2, then you check line 8, component U, component V. Are they different or are they same?
Same.
So I will not add it. If I added it, then it will become a cycle. Okay. Is this part clear?
No, which one will check, ma'am? Now, where the
1 and
cycle
2.
will
1 and 2. See this edge.
that age. Okay.
Okay. So both 1 and 2, these two nodes are now in the second component, right? 2 component. I have updated component value for all three
Yes.
nodes, 0, 1 and 2. So this condition will fail if component U is not equal to component V. No, they are equal. So I won't be appending the edge in my MST.
Okay.
Okay. So like this, you will do for every single edge present in this edges list. Okay. And wherever there is a possibility of a cycle forming, we won't be adding that edge because they will be in the same component. So after all of this is done, now this is the basic
Ma'am?
logic of, yeah.
Age will not be added, but the for loop will still run, and what purpose it will serve now?
This.
Yes.
So they are already in the same component, right? Oh, okay. I'm sorry. This is this for loop you're asking.
Yes, ma'am. now let's say the if condition has not been
So
true,
so that means C was also not updated, right?
not update, so it's previous one only.
Previous one only. So nothing will basically change here if you're not
But for
adding.
loop will run, no, for
Yeah, it
entire
will run. It will run. Okay, because we have to run this for loop
Okay.
regardless. But there won't be a change because C value was not updated.
So wouldn't it be better to put this for loop inside the if?
If you put this for loop inside the if, then some updates will miss. See, if I put it inside the if, okay, I'll show you in the end. Okay, when I do the test.
Correct. You can go ahead with the logic first, then yeah.
Okay, so this is the basic classical logic, how every edge are being selected. So we are starting from the smallest edge and then selecting one after another, because all the edges are sorted in the edges list now. So after the smallest, the second smallest, third smallest, like that we will select. And every time before adding, you will check if it is forming a cycle or not. And after that, you are always going to run this for loop also to update the components. Okay. So basically, see what is happening. After this, I need to return what? Now, what has been in this TE list? What has been added? All the edges that are going to be in the MST. Are all such edges added to TE?
Yes.
Yes. So I can return TE.
Yes.
So return TE. So Kruskal's logic is done. Now, how am I going to incorporate this in the actual function airport? So in R variable, what will be stored? TE.
MST.
Okay, the edges that are in the MST, list of edges. But my job is to find the distance, minimum distance, right? So I have to now look up the distance between all these edges. I have to now find the distance. The distance is stored where? In the distance map. Okay, so let's initialize a variable called S. Inside this, I'll store the distance. Now for E in R, means for every edge in R, for every U comma V pair in R. For there is a nested loop for, let's call it ED in distance map E0. First, tell me what is happening here in these two lines. What am I selecting? First, I'm selecting E, that is each edge from the MST, right, that we have found. So each MST edge U comma V pair. Now for each such pair, come inside the inner for loop. For ED in distance map E0. Okay, first tell me what is E0. Let's say this edge 0 comma 1. So E0 is what?
0.
0. In distance map of 0, what is stored? Like this. So a list is there inside. There are tuples where I can see that from 0 what all nodes I can go to and what is the distance. Right. So there will be definitely a tuple like this 1 comma 10. Will there be in distance map of E0?
Yes.
For the edge 0, 1. Okay. So for ED in distance map of E0. Okay. Why we have to iterate? Because there are multiple such destination vertices where I can go to starting from 0 vertex, right? So for each such destination comma distance tuple, take each of them. What you have to do is you have to update the distance, right? But what you have to check first, there are multiple V's. We are checking for U comma V. Take this E as, to understand better, take this E as 0 comma 1. Okay.
Ma'am,
First edge.
1 second. Distance map is going to give these tuples corresponding to only direct edges, no? Not like till
Direct
every.
edges. Yes, direct edges only.
So zero's distance map will be just
One,
about
zero,
1, 2,
one,
and
1, 2, 3. Okay. See in this graph,
no, only
0 to 3, there is also a direct edge, right?
correct. So zero's distance map will be for 1, 2, and 3. That's all.
Yes, 1 comma 10, 2 comma 50, 3 comma 300. These three tuples are there.
Okay.
So I have to iterate through each of these tuples now. So for ED in distance map of E0 is basically picking these tuples. So let's take the first tuple, 1 comma 10. So I have to match now. What is my actual u comma v? 0 comma 1. Okay, so I have to match that destination tuple matches or not, because I need to only pick the distance for that, right, for that destination tuple. So if ed 0, what is ed 0?
0. Sorry,
No,
1.
1, because the tuple is what? 1 comma 10.
Yes.
So ed 0 is giving 1, is equal to e of 1. E of 1 is what? Also what?
Distance.
E of 1 is the 1, right? Because E is what? U comma V, the edge that is in R.
Sorry. E.
Okay, that means the destination vertices, wherever they match, wherever they find a match. Okay, that means from 0, where I can get to 1. So there are multiple such destination vertices, like you just said, from 0 I can go to 1, 2, 3. So there will be 3 different tuples, but only one of them will match with E1, which is this, right? This one node. So wherever you find a match, that distance you will add. So for that ED, I will add the distance. So S plus equal to what? ED1, that is the distance. See, this is confusing, okay, because there are lots of things here. ED, first think of ED. What is ED?
Oh, ma'am, when we say E1, basically it's the destination which we are talking.
Correct. E0, E means U comma V. Now E of 0 is U, E of 1 is V. Fine.
Yes.
Similarly, ED, when I say ED, ED represents what? Every tuple for E0. That means every tuple for 0 basically in distance map. So only one tuple will have the desired destination vertex, right? That is this tuple 1 comma 10. So I have to match the destination tuple where the V matches. So E of 1 is basically the desired V, that is the vertex 1. So that will match with some ED, right? What is that ED? 1 comma 10. So ED of 0 is 1. So this match is found. So corresponding distance I will add. Every ED entry looks like what? 1 comma 10, 2 comma 50, 3 comma 300. These are ED entries. So ED of 0 is what? The vertex, and ED of 1 is what? The distance. So once the vertex matches with your MST edge, then you can add the distance to S. Is this part clear? These 4 lines.
No, ma'am, it is getting more confusing, ma'am.
Okay, let me start over again. See.
Ma'am, I have
Should I
understood
write?
till R is equal to Kruskal. Now after that, I am getting a bit confused.
Okay, let me.
Ma'am,
Yeah.
why can't we just take all the distances from R and just some?
So to find the distances, is R containing distance? R is just containing edges. U comma V format.
Yes.
Okay. See, TE we are appending U comma V. So these are just edges. Now corresponding distance is stored in the distance map. So that's why I have to go through every edge in the distance map also to find out the desired destination node and the corresponding distance I have to add. Now how I'm doing that?
Okay. Ma'am, basically what we are doing is we are identifying the edges and getting their weights,
Correct.
and then we are adding it.
So only I'm picking the U comma V edges that are in the minimum spanning tree, and I'm trying to find the corresponding distance between U and V using distance map. Okay, so these lines, anyone needs me to say what is happening here again? Line 23 to 26. I can explain this again. Anyone needs?
Basically, whatever edges are there in our Kruskal tree, we are searching it in our the entire graph.
In the destination map. Yeah. Corresponding distance we are adding.
Yes, got it.
Okay. Anyone did not understand this part? Please tell me now or I will not proceed. Okay, so I will take that everyone understood. Very simple. Just every E is an edge, and for every E you are checking every ED. for that E0th element. That means U comma V, right? So you're checking that for that U, whatever vertices are there. That means from this U, what all destination nodes are there. So I will check all the nodes until I find a match with my destination node in the actual MST. Wherever I find the match, the corresponding distance I will add. So this is just to find the distance between each edge in the MST. Okay. Because this is only going to give the minimum weight, right? Minimum spanning tree, I have to add all the weights, that is the minimum distance. So after S is...
Ma'am, could we are picking E from Kruskal output
Correct.
now and trying to just find out this E is already a tuple where there is a source and there is a destination, U and V,
Right.
correct ma'am?
Right.
Which were in our MST.
Yes.
So why couldn't we pick their distance in Kruskal itself? Like here
So in
it's looking
Kruskal,
like we are going
in Kruskal is the distance present anywhere. Whatever Kruskal is returning, the distance is not present there. It is just
D was
returning
there,
the
no,
edges.
correct, but there was a DUV. We were circling. I mean,
Yeah, so you are
scanning
saying
through
that in this part only I could have added the distances. That's what you're saying.
correct, ma'am. Because
So maybe in some way you can incorporate that also if you want. Then all you have to do is just return everything here. Just return that distance here. Okay, but then this airport function won't be doing much. It is just the Kruskal doing everything. Okay, but here if you want to add, right?
Yeah, ma'am, this getting a bit confused. Can you add in Kruskal itself?
How can I add in
because we are
Kruskal?
in,
See,
When you
I'm
append T of T dot
every time you're
append,
appending this T dot append U comma V, right?
yeah,
So that
then
particular distance you can add here also in S.
can we just append U comma V comma D?
U comma V comma D. So all three you want.
Yeah, can't we do that?
in Kruskal output. Let's
Yeah,
say
you
Kruskal
can do it.
team.
Okay. Definitely this
Then
can be done in a different way also. Okay, if we append all of them, correct? If we append U comma V comma D, and then we come back to this airport, and then we can just go through each of these and just add the third element in each
These,
tuple. Right? That would also be an easier way. I am discussing this because this was given in the solution itself. Okay.
Understood, ma'am. This why I felt of that solution because this for ED in distance, this function is doing nothing but Kruskal's T second
Yeah.
guy. Where is it there? That's where finding out.
It is just adding the same distances in the distance map. So you already have those distances here also because distance map was passed in Kruskal. Right.
Correct.
So that is also possible.
Okay, ma'am.
Wait, I think there is an extra for here.
That you typed when you were explaining
Typo.
something.
Yeah.
It was a typo.
Okay. So, but this solution is clear, right? What is happening in this one also. If you understand that, you will understand this also. Same thing is going on. Since I am not updating the distance in Kruskal itself, I have to find them in distance map now because now I don't have the distance in airport, right? After the Kruskal has returned, I have to check in distance map for every U comma V. Simple thing. So after this, after you have done updating the S, we'll just return it. So return S. You can also try doing that code. Check, test run if it works. I think it should work. Okay, so this one works. You can just change the code right here. I mean, after this T dot append, you can just change it to U comma V comma D, and then in S you can add the D. All right. Anyone has any doubt in this problem, or should we go to the next? Okay, let's go to number 2.
What I'm finding difficulty in believing is how component update will stop at 2. You took an example of 0, 1, 2, na? Cycle, forward cycle formation.
Yes. So it is not stopping. Okay, it is not stopped at 2. Okay, for that D comma U comma V, it is 2. Now the next D comma U comma V will be picked. So there the components U and V are different. Okay, now we are going to update for those components. Now the edges where the update is where we are not appending to TE because the cycle is forming, right? So their C is also not updated. So let's say, for example, this one, 1, 2. This edge is not added, right? Because they are both in the same component. So if condition fails, but this for loop will still run. So for every key, what it will check is wherever the component W matches with C. So C is still the previous C, whatever it was. Okay, nothing is different. The previous C was 1, right? So again, 1 is just reassigned 2. Nothing is changing here. It will only
No, no,
change.
no. What will happen if 0, 3 is being checked out? Like,
So 0, 3, right? So that is the next D, U, V pair, this pair. So that is
okay, that time
300, yeah, 300, 0, 3. Now your components are different. 0 is in component 2, 3 is in component 3. So C will be updated also.
so in short, we are restricting the component building only for 0 in the first iteration.
Let's say there are also edges between 1 and 3, right? So one pair will be like this also, 40, 1, 3 for this 1, 3 edge. But the component of 1 and 0 are same because they are having an edge between them. Okay, it is not restricted. For every pair, it will check the components, but the component has to be updated every time you add an edge.
Correct. So when 3 is being explored, 0, 1, 2, and 3, all of them will have same
All of them
component.
will have same component. So then the component will be what? 3. Component of 0 will also be 3, 1 will also be 3, 2 will also be 3, 3 will also be 3. Because we are always changing the component to the destination vertex, the current destination vertex, right? Component V.
Correct.
Okay. Alright, let's go to problem 2. So this one is based on Kruskal. Now the second one I think was Dijkstra. Yeah. Okay. So you are given a network of n nodes labeled from 0 to n minus 1, and you are also given travel times, which is a list of signal travel times in as directed edges. Okay. So first of all, there are n nodes, and travel times is a list. Okay, which is like this. So in travel times, for every I, that is for every node, this thing is present: ui, vi, wi. Okay, so these are the travel times. Basically, it's a list of tuples again. So where u is the source node, v is the target node, and wi is the time that it takes for the signal to travel. So same thing, think of it as the cost or the distance between u and v. Now we have to write a function called minimum transmission time, which takes the number of nodes, the travel times list, and the source node s. Okay, and this does what? It returns the minimum time required for the signal sent by the source node to be received by every other node. That is, there are n nodes, so the source node sends out a signal. What is the minimum time in which every other n minus 1 nodes would have received that signal? So that's what we have to find. So this is what type of a problem? Single source shortest path. Right. So we can do it using Dijkstra. Again, there is one more thing, that if it is impossible to find to obtain such a signal for all n minus 1 nodes, it might happen that the signal is not reaching every node. In that case, you have to return -1. So this is the sample. So Dijkstra is also another greedy algorithm, right? What it does, single source shortest path, what happens in Dijkstra? Anyone can explain just briefly what it does?
Dijkstra, it keeps two sets. One is like visited and one is like not visited. And at every step, it goes to the vertex, which are like not visited yet, and it gets the minimum distance from that
Right.
single source we have.
Correct.
It keeps updating.
So that means at every step, the greedy decision is that it will pick the closest vertex, closest unvisited vertex. Right, that's the greedy decision. So that same thing we are going to apply here. So 3 things I have to take as input. One is the number of nodes, that is n. Another is the travel times. Okay, the same thing as the previous one. We are calling it edges. This is the travel times list basically. S is the source node. And then we see here it is written minimum transmission time. It is passing these three as argument and printing whatever this returns. So we have to first write minimum transmission time. We also have to write the another function for Dijkstra. So let's define minimum transmission time. What all is it taking? N. Let's call it travel times. That is this edges. And S, source vertex. So first thing I will do is let's create something called an A list. Okay. So A list is an empty dictionary. Now inside that, I'll first write the loop. I think you will be able to decode what it's doing. If you can't, I'll explain. So for I in range n, that is number of nodes, A list I. First I'm assigning empty list. So in A list, what are the keys? Each node. Correspondingly, values stored are empty lists for every node initially. Now let's populate A list. Okay. So for U, V, D in travel times. That means this UI, VI, WI. For this U, V, D in travel times, every such triplet. Pick it. In A list, we will append what? A list for U. Okay. We'll have dot append V, D. So that's same thing like the previous one, right? That for every source, the destination and distance that is stored in a list of tuples. Okay. After this, we have to define. Let's call two variables, distance and INF. That is infinity. Okay. Now here I am going to call the Dijkstra. So let's call it Dijkstra list. I'll pass the A list that we created and the source vertex. Now before I finish this transmission time definition, let's now create the Dijkstra definition. Then I'll come back to it. Yeah.
Why do you need INF? It's used in Dijkstra's algorithm.
Why do I need what?
And why do you need INF?
N is taken as input. That is the number of vertices that are there.
No,
Number of nodes.
INF. So generally, Dijkstra's algorithm we return.
No, in Dijkstra's, I'm not passing N. I'm just passing the A list and source vertex. Okay, N is in the minimum transmission time.
No, when we run a Dijkstra's algorithm, it we just
The
return the
return
distance
value.
dictionary.
He's talking about the return value, INF.
INF. Okay. INF. That you will see what is INF. I'll write that. I haven't written yet. Okay. Let me define Dijkstra first, then I'll tell you. So define Dijkstra list. This one is taking, let's call it W list to have the similar vibe as the last problem. And S. Now I will define something called infinity. So infinity, how can I define? Let's just calculate some value that is very big. Okay. That will not be the signal time for any node. We have to create such a value. So if I create this value, see 1 plus length of W list dot keys. Okay, length of W list dot keys, and then let's take star. That is, I'm multiplying with this the maximum distance. So D for U in again W list dot keys for V, D in W list of U. Let me take this in the next line. So the value that is formed here, is it possible to get a signal time that is higher than this for any node? So I did what? I multiplied the length of, that is the number of keys, number of nodes, with the maximum distance that any node has between any two nodes. I'm taking the maximum distance. For all v comma t pairs, I'm checking the distances, I'm taking the maximum one. So if I multiply that with the number of nodes that are present plus 1, is there going to ever be a value which is greater than this in the transmission time distance?
No.
No. So this is some arbitrary large value. So I am assigning that as my infinity, because you all know that when I start the Dijkstra algorithm, only the edges which are directly reachable from the starting vertex will have the distances, right? Others are all infinity. Initially, everyone is infinity, right? Including the start vertex, every vertex is going to have infinity distance. So that's why I need an infinity. So I created it like this. Now, after this, let's take visited, a dictionary, and another dictionary called distance, because these two things we have to maintain. Which nodes are visited and what is the distance, current distance for a node. So two dictionaries. Now let's initialize. Now let's assign the visited and the distance for all of these nodes. Okay. So initially, no node is visited. That means visited should be false for every node. And initially, what is the distance for every node also?
Infinity.
Infinity. Okay. So write a for loop for v in W list dot keys visited v and
Oh,
distance.
ma'am, in line number 3, you forgot that colon.
No, this is all inside the same thing, right?
Ma'am, I think you have to give a backslash in the line number 2, so that
This one.
in the line number 2 at the end, so, so
Oh,
that
this is
you can
not, this is taking as a separate for. No, these are all
yeah,
inside the parenthesis, right? It is the
inside
same
number.
parenthesis continuing up to here. Okay, let's see if that gives an error, we'll check. Okay.
Okay.
Okay. So first let's do the visitor and distance for every node. So for every node, initially it is false, visited is false, and distance is the infinity. Now, after this is done, we have to start with the source vertex that is given S. So what is the distance of source vertex in Dijkstra?
0.
0. So let's update. So distance of S is updated to 0. Now, for who is joining so late? Wait. Is someone trying to join or I can't see. Okay. So now let's go through all the nodes. Now tell me in Dijkstra, every edge is relaxed or every node is relaxed how many times? We understand what is relaxation, right? So if a node, let's say I want to reach node 3 from node
Only the
0.
non-visited nodes will be relaxed. Visited won't be.
Yeah, non-visited nodes. But I am just asking that every edge in a Dijkstra algorithm, so you have studied the algorithm
Once, only once.
only once, right?
Yes.
So we have to go through, we will check for how many times. The for loop will run as many times as there are nodes. So for you,
n times.
sorry, come again?
N times.
N times, correct. So for u in W list dot keys. Now we'll write the Dijkstra logic. So Dijkstra logic is what we always take the edge or the distance which is the vertex which is at the closest distance and unvisited, right? The shortest distance unvisited. So first let's find out that distance. Okay, what is the shortest distance? So let's call that next d. So inside next d we'll find the minimum distance. So minimum distance v. Okay, distance v for v in w list dot keys. That is for every node we have to check the distance. Another condition, is there another condition?
It should not be
Not
visited.
visited.
If not visited v. This is correct.
Yes.
It will give the minimum distance between among all unvisited nodes currently. Okay. Next we have to now create a list. Okay, a list for such nodes which are at the minimum distance. Now there can be more than one node which is at the minimum distance, right? So let's form a list. So next v list, call it. So v for again v in w list dot keys. If not visited v, if that is true, and distance of v is what?
Next d.
Next d. Okay, so this will create that list. Okay, let me take this in the next line. This is okay, I think. This is oh, here also I need to do this. I think this will work. Okay, so this is the list of nodes that are at the minimum distance, current minimum distance. Now I have to pick one node, right? Because at a time I can pick only one node. So that will be what? That will be picked according to the node IDs, basically 0, 1, 2, 3. Let's say 1 and 2 are at the closest distance, so I will pick node 1 based on the node ID. So for that, just call it next v. That is the next one that I am going to pick, next node. That is minimum of what? Next v list. These three lines, is it clear what is happening here?
Yes.
Okay, so next d is having the minimum distance, current minimum distance from the source node. Okay, so among every node, basically, what is the minimum distance currently? Now there can be more than one such nodes which are at minimum distance, so we have to form a list. That is the next v list. Now we can only pick one node at a time, so we'll pick the node that has the minimum ID. So let's say 1 and 2 both nodes are at minimum distance. I'll pick node 1. So for that, next v is containing minimum of next v list. Okay, up to now I have done just this. Now once you have picked the next v, okay, that is, this is the now current node. So now visited has to be changed. So visited of next v will be updated to true. Okay, now what I have to do? For v comma d in w list of what?
Next d.
Next v, because this is the node I'm exploring. Next v. If now I'm checking that if it is not visited, okay, if it is not visited, only then. So if not visited v, if that current node that we have picked from every v comma d tuple for next v, if the node is not visited, then distance will be updated how? This is the relaxation part. So distance of v will be what? Minimum of two things. First is what the current distance is. If the current distance is smaller, we'll keep it. So minimum distance v. If it is not, then it is distance of next v plus something. What is that?
D.
D. So whichever is the smaller one, that I will assign to B node distance. Right, this is the edge relaxation or node relaxation, whatever you want to call it. So this thing will be done for every node, right? This V comma D will be checked for every V, all V comma D pairs. So this thing will be relaxed for every unvisited node. The whole thing will occur how many times? The entire loop will run n number of times if there are n nodes. Okay, and every time, I mean, a node can be relaxed only once, because see, once it is relaxed, this will not be true again, right? Because visited V will now be set to true. After this, the visited V will be set to true. Okay, so only once we are going to relax. Okay. So after this is done, we can return. So return distance, and I'm also returning the infinity that I created here, this line 2. Why am I returning this infinity? Because later on when I go and check the maximum, the minimum time required, right? So there I'll be using this infinity. I'll show you how. Is the Dijkstra algorithm itself clear how it is written? In this function, anyone has any doubt? This part. See, this part is the actual logic, right? So once we pick a node, now we explore every other node that we can reach from there, and we change the distance based on whichever is the minimum one. So if the current distance is the minimum one, it will take that. If I can relax that, then I will relax by using this formula distance of next v plus d. So let's say I want to travel from, no graph is given here. Okay, no problem. Let's say I want to travel from 0 to 1. Okay, so 0 to 1, there is a direct edge. Okay, so 0 is the source vertex. Let's say 0 has distance 0, obviously. Now from 0 to 1, it takes distance 10 or time 10, whatever you call it. The cost is 10. And the 10 node, and the one node actually has a cost of 20. So which one is better, 20 or 0 plus 10? So 0 plus 10 is better, so it will be relaxed using that. Okay, so this will happen for every node once, at most once. Now after this is done, the distance is updated, right? Here in line 18, the distance is being updated. So the entire distance dictionary is after this is now updated. So nothing more can be relaxed. Then you return it. So return where? To this min transmission time. So distance, this variable dist, it is containing the distance dictionary, and INF is the infinity value. Now what is the question asking me to do? The function returns the minimum time required for the signal sent by the source node to be received by every other node, if it is possible to obtain a signal for all n-1 nodes. Okay, if it is not possible, then you return -1. So now I'll have to write the logic for that. So let's take a variable called max time, in which I will store my time. Okay, the minimum time required. So for every node distance pair, okay, node comma distance in this distance dictionary, so distance dot items, if the distance is greater than equal to max time. If I find a greater distance, then what should I do? I should update max time. So max time should be the current distance. Okay, what is the other case? If it is not if the current distance, so after this part executes, after this, just this part executes, max time will contain what? For every node comma distance pair, and checking whether the current distance is greater than what is stored in max time, and according to that max time is being updated. So max time at the end of execution of the for loop will contain what?
The maximum time of all
Among all nodes, what
all
is the
nodes.
maximum distance or maximum cost, right? So that is the highest time that it will take to reach every node. The signal will reach every node by that time, right? Now, that is one case. If I find it, very good. But we have another case also. So let's say if some node was never relaxed, right? Because we did not reach there. So in that case, what is the distance of that node?
-1.
No, I'm asking what is the distance of the node? Infinity, right? It was never relaxed. So initially all the distances were infinity, so it is still infinity. In that case, that it basically means what? That not all nodes can get the signal. So in that case, I have to return -1. But what is the condition? That if max time, so max time is updated anyhow. Max time will be updated for every node comma distance pair. So in such a case where a node was never relaxed, so it was still infinity, max time will become infinity, greater than infinity actually. So if max time is greater than equal to INF, if this is the case, then return -1. Else part will return what? Max time. Anything else I need to do? Anything else I'm missing? Just check the functions once. If anyone has a doubt. Okay, let me run once. Let's see if there is any error.
It passed for me.
Okay, let's check. Yeah, it is passing. Okay, now ask me any doubt in both the functions. Anyone?
Ma'am, we can just get the values, and then return the max. If that is equal to the INF, then we'll return -1, else max time.
If, sorry, come again, I didn't understand.
I'm saying we can just get all the values.
All the
of
distances
distance.
and then check if that is infinity, right?
Yeah, we can just get the maximum. If that is
Greater than equal to
INF,
infinity, then you can return -1. Yes, that is also fine. Okay. Any other question, or should we do the last problem? Okay. So the last one is pretty easy. So now you have done one problem on Dijkstra, one on Pascal. Also, you can practice the Prim's algorithm also, right?
Ma'am, in OPPs, such questions will come. Then
Yeah,
how
yeah.
much time will be given for entire thing?
How much time in PDSA OP grading document you have checked? How many questions are going to be there? I think it's a total of 3 hours or something. The exam is.
Okay, I think there are 4 to 5 questions. I don't remember exactly.
Yeah, 2 hours or 3 hours, something like that. Okay, I'm not entirely sure. I'll have to check the grading document once. You check it; it is all given. Okay. All right. Now see
Ma'am,
the.
excuse me, ma'am. Ma'am, can you show the code once? Complete code?
Yeah. This. Oh, complete now. Wait. Okay.
Thank you, ma'am.
Yeah. Okay, now last problem. Here most of the other codes are written prefix suffix code. So we just have to write one function. Okay, so the first read the question. An airlines company has flights operational in n cities, level 0 to n-1. we have to write a function called best fare. Okay, best fare function will take four different arguments. Sorry. One is the flight route, that is again another weighted adjacency list. Another is the source, another is destination, and a variable k. So what is happening? Basically, three integers are there. Okay, one is the source node, one is the destination node, and k is some positive integer. So function will return what? It will return the minimum cost and the flight route in such a format, this, as this. Okay, minimum cost, comma, source, next stop, next stop, next stop, like this, destination. So how many stops in between? K stops. Okay, basically what we have to find is what is the minimum cost flight route between a source node and a destination node, having at most k stops in between. K can be anything, 2, 3, 4, anything. Okay, but at most k stops. Now in this case, source and destination are not included. These are the intermediate stops. Okay, source, destination are not included. So you have to find the minimum cost and the flight route for that, such that there are at most k stops in between source and destination. If you don't find such a route, then you return not found. Is the question clear?
Oh, ma'am, can you repeat once, ma'am?
See, there is all these flights. Okay, again, so flights are going from a source to a destination like this, and there is some price associated with it, which is the cost. So our function should give us what we are giving input: one source node, one destination node, and some positive integer k, right? So the function should return such a flight route where the flight starts at source, ends at the destination, and has at most k stops in between. Okay, so at most k cities it has visited in between the source and destination cities. And
It can be less than k.
Yeah, it can be less than k, at most k. Okay, and we should find such a route which has the minimum cost. Okay, so now let's check the inputs once. So if this is the input, so number of vertices, let's say 5 vertices, so 5 cities are there. These are all the edges, so you can go from source 0 to destination 1 at a price of 1000. So these are all the direct edges. Basically 0 to 1 there is a direct edge, 0 to 2 there is a direct edge. What are the different costs associated with each edge? So that is given in the edges list. 0 is the source, 4 is the destination, k is 1 in this example. That means you can have at most 1 stops in between. So either you can have 0 stops or you can have 1 stop. Okay, the output should be like this. So just by looking at this list, you can see that I want to go from 0 to 4, right? So 0 to 1 there is a route. Now from 1 to 4, can you see a route? No.
1 to 3 is there, and
1 to 3 is there, 3 to 4 is there. So if I take this path, then what is the total cost? 0 to 1000, 1 to 3, what is it?
300.
300. So that is 1300. Then 3 to 4 there is 1. Right.
1900.
Now how many intermediate happened? 2. 1 and 3. But what is my k? 1. So is this a valid route?
Oh, ma'am, intermediate means from we already have destination now, ma'am. Source and destination.
Source and destination are not included in k.
Okay.
Only the intermediate one. So from 0 I travel to 1. So that 1 is the intermediate node. From
Yes.
1 I travel to 3. 3 is intermediate node. So there are now 2 intermediate nodes, which is invalid because intermediate node can be at most 1 in this example. So let's take a different route. If you go from 0 to 2, okay, that takes 500. From 2 you can directly go to 4. Yes, that takes 2000. So what is the route? 0, 2, 4. Okay, k is 1, which is valid. And what is the cost? 2500. So that is the minimum one if you find. That's the output should be in this format. Understood? The problem is clear.
Yes, ma'am.
Okay. Now see this, if you want me to describe this code only, then I will, otherwise I'll directly write the program. What is happening here, I'll tell you. So this suffix code here, you have just taken the inputs, right? The number of cities, the edges list, source, destination, k, and then again you create a W list. As all previous problems, just create the W list. It is taking what? First, initially for every city, again take an empty list and then append like this. So from 0 city, I can go to city 1 at a price of 1000, right? Same as the previous problems. But it is going to print whatever the best fare returns. The best fare I have to write. Now, what are these two things? These two definitions. Find all path. Okay. Now see, in our question, I can see from this example only that from 0 to 4, if 0 is my source, 4 is my destination, there are multiple paths between 0 and 4, right? So first I have to find every possible path. Then I have to put my conditions on it that, okay, this is the maximum number of K that you can have, maximum number of intermediate stops that you can have. What is the minimum cost? So there might be more than one such path where the maximum number, where the K is valid. That is, the intermediate stops are less than equal to K. So there can be multiple such paths between my source and destination. Once I figure that out, that which are the valid routes, then I have to figure which route is taking the minimum cost. Okay. So to find all of this, first I have to find all possible paths between source and destination. Correct. So that is what I'm doing in this find all path function. Okay. Now find all path, you can see it is creating what? So initially this visited, it is creating another dictionary called visited and a list called all path. So visited dictionary, all V's are initially false because no node is visited initially. And all path is empty. Another list is taken path, that is also empty. And then it is calling another function called add all path, where it is passing the current W list that we created, source, destination, visited, path, all path, all of this. So this is the main function that is doing, that is finding the paths. So if you just look at this, can anyone tell me what algorithm is this? You don't even have to decode. First look at the problem. If I say from 0 to 4, I need all possible paths. What algorithm am I following to find that?
Also shortest path.
No, I am asking all paths between 0 and 4.
Oh, single source.
It's not even all these difficult things. It's a very basic thing that we learned in graphs. What are the two ways of graph traversal?
BFS.
BFS and
So this is BFS.
This is DFS.
This is a DFS.
So you go from 0 to 1, then 1 to 3, then 3 to 4. Right, I am not exploring at every level. I'm exploring the depth. Another path you have to find 0 to 2, 2 to 4. Right, another path can be 0 to 2, 2 to 1, 1 to 3, 3 to 4. These are all DFS traversals? Yes or no?
Yes.
Okay, first you have to understand the difference between BFS, DFS. So if you are still confused on that, first you clear that concept, then you understand this. Okay, DFS means that I am not exploring all neighbors of a node at once. Okay, I am reaching the depth, the most depth that I can reach from a node. So if I start from 0, what is the most depth I can reach? From 0 I can go to 1, 1 I can go to 3, 3 I can go to 4. Can I go anywhere more from 4? No. So this is a DFS path, right? So this DFS algorithm will give me all possible paths. So that is what is happening in this add all path. Okay, add all path is just a DFS procedure. So DFS, if I want to find all possible path, is recursion required?
Yes.
Yes, because see, when I come to node 0, my source node, I have two choices. Either I can go to node 1 or I can go to node 2. So if I start to go to node 1 and then I explore node 3, then I explore node 4. So when I backtrack, I again have to come to node 0 and search the other path, right? That is from 0 to 2 and 2 to 4. So for this, I require recursion. So that's why you can see that there is another procedure call in line 10. So for every unvisited node, we are calling the add all path. This procedure, do you want me to define, or can you understand it on your own?
Ma'am, basically I'm stuck with the graph, ma'am. This graph indicates what, ma'am?
This graph is just the paths, the routes. Okay. See.
So, ma'am, if I wish, I can take 2 as my start node.
Where do I start? The start is
Ma'am,
given to me, right? U.
okay.
So that is where I'll start. So
Okay.
let's say whatever input you have given, if I have given input 0, so in this example I've given source 0, so I'll start from source 0, right, and I'll go till
So what I
destination
am
4.
doing is I'm taking my source as 0 and I'm searching for all paths
I'm
to
taking
all.
my source as 0, I'm taking my destination as 4. See, both are passed in the
Okay,
argument,
okay,
u
okay.
and d,
Both are given to
and
me.
I am finding every possible path between these two.
Okay, okay. Got it, man.
So this DFS traversal is only given in this part. Okay, so does anyone need me to define this? If you need, I can do it. Otherwise, I'll write the program. Okay, anyone wants me to explain this procedure, add all path? See, I'll just say briefly once what is happening here. So you first check. First, what do we do in DFS? Okay, first I will check that is my source and destination both same. In that case, there is no path, right? I'll just add the one node, the source destination, if both are same. Otherwise, I'll do what? I'll check that, okay, source destination are different, so my source is let's say 0. In that case, I'll see in W list of 0, from 0 what all nodes I can visit. So I can visit 1, I can visit 2, like this. So I will go through all of these. Let's say I first take visited I of 0, let's say that is 1, so node 1. So is node 1 yet visited? No, so it is false, right? In that case, you are again going to call the same procedure add all path. Here now your source node becomes 1. So 1 to 4, now you're finding the paths. Same again, you go to 1, you try to explore 1. So from 1 you can go to 3. So 3 is again unvisited. So you again call add all path. Now your source node is 3. From 3 to 4, how many paths are there? Only 1. Okay. 4 is visited. Is it visited? No. Again call this same procedure. Now your source and destination are same. Both are 4. In that case, you just add it to the L. That is the path. Okay. So path, see all path dot append L. So in path, you are going to append the 4 like this. So you have to backtrack, right? Every time you're visiting a node, you're appending it to the path. Okay. So that you know that these nodes I have visited while creating the path. So this is the DFS traversal. After this is done, the the all path list, that will contain what? What is this all path going to contain? See, that is what is returned.
Path from source to destination.
It is a list of all possible paths from source to destination.
List of lists.
Is it a list of lists? All path is having what? Append L. Inside L, I am just making a copy of the path. Path is what? A list. Path was initialized here, right here in line 20. So it is a list of lists. What is this list of lists? Every possible path from source to destination, right? So the format of return list is like this. So these are what? All possible paths. Every element of this list is a list which is a valid path. Now after all this is done, the find all path will finally return the all path, okay, for the given source and destination that we have taken as input. Now our job is to find the best path, which has to follow two conditions. First condition is that number of intermediate nodes between source and destination should not exceed k. Second condition is I need the minimum cost, the path which has the minimum price, minimum cost. So these two things. So I'll write the function. So it is define best fare. This is pretty straightforward. So all this code will be given to you only. You just have to figure out what it is doing, right? So flight route, it will take the source node, destination node, and k. Okay. So let's take a variable called L. Inside this L, I'm calling the find all path. So again, pass the same things: flight route, source, destination, nothing else. We don't need k here, right? We just need all possible paths. So in L, what will be stored once this find all path has executed?
List of all paths.
The list of all paths. So this all path basically, this list of lists. This is stored in L. Okay. That is every possible path from source to destination. Now we will put our conditions on it. Let's say the source and destination that I have provided, there are no paths between them. If I give 2 to 0, is there a path between 2 to 0? Yes, there is one. Okay, let's take a path which is not there. 3 to 0. In case
No
of
path.
3 to 0,
No path.
what will all path contain?
Nothing.
It is an empty list.
Yes.
Correct. So first I will check for that, because it is possible that there might be no paths. So if L is not equal to empty, if L is not empty, only then we will proceed. Okay. So first let's define an arbitrary cost which is very big, just like that infinity we defined in the last problem. So we will then check which cost is less than this, and then again less till we get the minimum cost. So first let's define that arbitrary large cost. So cost is 1 plus, let's take length of flight route. Wait, flight route, are they using a hyphen or not?
Underscore.
Underscore is used, right? Okay, flight route. Length of this flight route dot keys. So every key in this, right? That is every node. Into
Ma'am,
again.
in line number 24 also flight route. The underscore.
Okay. Yeah, thank you. Okay. Multiply this with the max of what can we take? That distance or the price, right? So let's take for D for U in flight route dot keys for V comma D in flight route of U. So this is that arbitrarily large cost. Fine.
Ma'am,
Yeah.
I can just take float of INF, and this is taking.
What we can take?
You can also take float of INF.
We
That
want
will
some.
save time.
We will take some cost which is never going to be generated. Okay, it should be that large. So I am taking the number of cities multiplied with the greatest price. So it cannot be larger than that.
Yeah. So float of INF also gives some infinity.
Yeah, but I haven't defined infinity here, no? That's right. That was in the previous problem. You can do that also. It's fine. This is the infinity only. Okay, it is just I have taken a different variable called cost, but it is doing the same job. Now the cost is set to something very high. Okay, but we need cost to contain the lowest cost, minimum cost of a valid route. So now we also have to return the route, right, in our result. So now let's initialize a list called route. Okay, now start with the conditions. So for, let's call it PTH in L. That means for every path in L. L can contain more than one path, right? Between source and destination, there can be multiple paths. So for every path, we are going to check which is the valid path. So for path in L, so what do you think should be the length of the path that it should not exceed?
Less than k.
Should it be less than k? I am asking about the entire path. K is intermediate nodes.
K plus 2.
So k plus 2 is the highest, right, or the longest that a path should be if it still needs to be valid. That means I can write that if length of path is let's say less than k plus 3, this is Okay.
Yes.
Okay. So that means the first hurdle is crossed, that path is valid. So it has intermediate nodes at most k. Next thing, x is, let's take a variable s, which is set to 0. Now again run a for loop. So for I in range 0 to length of path -1. Okay. So it will run in this range. Inside this, I need one more nested for loop. So for j in flight route path I. First, let me write, then I'll explain. Okay. If path of I plus 1, that is the next node, is equal to some j of 0, in that case, I will add the distance or the price. So s plus equal to j of 1.
Ma'am, line number 32 colon missing.
Oh, yeah, right. So this will be shifted. Okay, so what is happening in these 4 lines? Basically, now I have a valid path. Okay, the current path that I have picked is valid. Now I am going through every node in that path, starting from the source node. So the range is from 0 to length of path -1. So I want to go till the second last node. Correct. Why the second last node? So basically I will pick every node. Then I'll go to the nested for. In that I'm checking for every j in flight route of that node that I've currently picked, the I. So what is path of I basically? If I is 0, path of I is the start node. Correct? Source node. For I in range 0 to length of path -1, if I is 0, then path of I is the start node or not in that path?
Yes.
It is the start node. That means path of 0. That means 0th entry in the list. That is the start node, source node. So for every node in flight route, this is the format, right? Destination, comma, price, a list of tuples like this. So now for the source node also, the 0th node also, there is such a list of tuples. Now I'll go through every tuple in that list. So this j is every tuple. Okay. Just look at this graph and tell me, for 0th node, is there a tuple called 1, 100? 1, 1000, I'm sorry. In flight route dictionary, for 0th node as key, in the list, in the corresponding list, is there a tuple 1, 1000?
Yes.
Is there a tuple 2, 500?
Yes.
3, 3000? All the direct edges from 0?
Yes.
Okay. So I'm going through each of these tuples. Which one will find a match? Which is present in our path.
Okay.
Right. Let's take the example that is given. So from 0 to 4, I want to travel. So let's take the correct path that we actually got. So 0 to 4. Okay. So think that we have taken this PTH, the current path is the actual path in the result. Okay. So 0 to 4. So starting node is 0. Right. So for I in range 0 to length of path -1, I is currently 0, first iteration. For that 0, what are the corresponding j's? One is 2, 500, one is 1, 1000, one is 3, 3000. In our path, what is the next node? 2. So path of I plus 1 is 2. Correct? Path of I is 0, path of I plus 1 is 2. So where will it find a match? With which j? Which tuple? 2, 500? See, I'm talking about this result. 0, 2, 4. This is the path that I have currently picked. Okay. What is the initial node in this path? Starting node? 0.
0.
So when I is 0, then path of I is the 0th node, correct?
Yes.
From 0th node, if I put the 0th node in flight route, against this 0th node, what are the values stored? 1, 1000, 2, 500, 3, 3000, correct?
Yes.
So each of these tuples I have to match. That which one is matching with my current path. So in my current path, what is path of I plus 1? I is 0. I plus 1 is 1.
2.
So
Vertex
2
2.
is I plus 1. So vertex 2. So will I find such a J0 where there is a match? Yes. When I pick this
0
J,
to
2, 500. Then J of 0 is 2. Correct. So there exists such a path from 0 to 2. Once that is confirmed, so this confirmation is done in this line 33. Okay, that means there is such a path from 0 to 2. Now I will add the price because I need the minimum cost also. So what is the current J? 2, 500. J of 0 is 2, J of 1 is 500. So just add the J of 1 to S. So 500 is added to S. Clear? Now see, in the next iteration, let's take the next I. So our next I value is 1. Okay. So for I1, find all the possible J's. So what are the possible J's for node 1? From node 1, which all nodes can I go to?
3.
So I can go to node, I'm sorry. Path of I is 1, path of I is 2. Correct. I is 1, path of I is 2. This is at the first index, right? 0th index, 0 is present, first index, 2 is present.
So we are at 2 right now.
We are at 2 right now. So from 2, which all nodes I can go to? I
1
can go
and
to
4.
1 and 4. So what are the possible J's? 1, 3000, 4, 2000. Correct? These are the possible J's for node 2. J's are the tuples in flight route for 2. Okay.
Ma'am, why didn't we consider 2 back to 0, ma'am? 2 to 0?
Okay, yeah. There is one more path also, 2 to 0. Yes. 0, 2000. That is also one J. Okay, every direct path is a J. From 2, whatever direct paths are there, all are J's. Okay, valid J's that we are going to search. So we are going to go through all these tuples. 0, 2000, 1, 3000, 4, 2000. Fine. But where will I find a match? What is path of I plus 1 now? I is 1. 1 plus 1 is 2. Path of 2 is which node?
4, okay.
Node 4.
Next in the list.
So 4 node will find a match in which J? In which tuple? 4, 2000.
Yes.
So what is the price that is going to be added to S now?
2000.
2000. So the total cost becomes 2500. Go for the next iteration. Can we do another iteration for I? No.
No, ma'am, list is empty.
Because we are searching only till the second last node, right? We are only going to do till the second last node. The iterations are going to stop there. So length of path minus 1.
So we will not consider 4 in the
No,
given.
because you don't need to check for 4, right? 4 is the destination node. You have to stop there. Okay. So the same thing will work. Okay, I just took an example. The same thing will work for every valid path. So for every path which has number of nodes less than k plus 3. Okay. For those, we are going to check this I. For every valid path, that means initially, if I, okay, let me check if there are more examples. Okay, let's say there are 2 paths. Okay, so 0 to 4 there is one path. Let's say some another path is also there which is valid. Okay, it is valid with the k that is given. So in both cases we are going to do this same thing. We are going to find the S. So now once you find the S, you have to compare with what? So we have to keep updating the S, right? If there are more than one paths, we have to find the minimum cost path. If there are more than one valid paths, we need the minimum cost path. So in that case, next step should be what? If the current S is less than cost. Remember the cost we defined. If current S is less than cost, then cost will contain S. Cost will be reassigned to the current S, and route will be reassigned to the current path. No, sorry, wait. Route will be reassigned to the current path.
Ma'am, again a typo, ma'am. Cost is equal to S, ma'am.
Cost is equal to S. Yes. Okay. Now again, when you go for the next path, you check the next path. Again, S, you might find even a lower cost, right? So again, you do the same comparison: is S less than cost? So you again reassign S. You again reassign cost. Again reassign the current route. Okay. So like this, we are going to do till we find the minimum cost and the corresponding route for that. But that is not the end, because again, there is a possibility that we might not find any route from the source to destination, right? So come out of this outer for loop. So here you will check if, so tell me, if there are no routes, in that case this route will contain what? An empty list.
Yes.
So I will check if route is not empty. Okay. In that case, we will return what? What is the return?
Route.
Cost and route, both, right?
Okay.
Cost, comma, route. Fine. What is the else part? Return. If route is empty, that means I did not find any valid routes. It can be possible that we found routes, okay? We found routes from 0 to 4, but those are not valid because they are not satisfying this condition. The intermediate nodes are greater than k. In that case, they are routes, but they are not valid routes. So we have to return what? Not found. Again, see, there was one if condition here in line 25, right? That if there were no paths also between source and destination. What did I say? This return not found is for what? Which case? If there are paths, but they are not valid paths. Now, if there are no paths at all, like I said, from 3 to 0, there are no paths. In that case, the list L itself will be empty, right? So we don't have to check all of these things. We can just come out here and write another else statement against this if. And just return not found. So if there are no paths, there is nothing to check.
Ma'am?
Yeah.
Ma'am, in all the cases, can't we say that we'll return cost and route itself?
But why do you want to waste all that memory, right? If you can just do that in two variables. So if you want to do that, then you have to return a list, right? But here I can just update two variables, cost and route.
Yeah, ma'am. What I'm saying is, in all the cases, whether there is a route or there is no route, shouldn't we just return cost and route itself, because they will contain the
So
entire.
if there are no routes, then what will you return?
So my cost will be empty, no? Sorry.
Cost will also be empty. If there is no route, there is no cost calculated.
Ma'am, it will be infinity, no? First line is itself. Cost
Yeah. So the cost is this, right? So it was never updated if there are no routes. Fine.
Yes,
We will
ma'am.
return this value only.
On that basis, we can. Okay.
Yeah. What do you want to tell me?
I just wanted to return cost and route rather than saying not found. No.
Yeah, that I am only doing because that is given in the question. Okay. So if there is no such route, return not found.
Okay, ma'am.
Okay. Is this logic clear? This if L is not empty, this part. Anyone who did not understand? Clear for all, right? Let's do a test run. Yeah, this is okay.
Can we just return one not found at the end?
You mean this case you want to
Yes.
remove?
Because either it will return the cost and route, or otherwise it will return not found.
So if this case, if I remove and you see that there are multiple routes, right? There are multiple routes, but none of them are valid. In that case, route will remain empty. So what will you return in that case?
Can we like break it or something?
But you have to
Ma'am,
print
what we
according to
can
what
do
is
is
given
we
in the
can remove,
question.
ma'am,
Yeah.
what we can do is we can remove both the else, and just after if we'll return not found, because we are out of the if, or otherwise we would have returned that cost and route itself. Ma'am, we can do it later, ma'am. I understood what
This
you are
part you
trying.
are saying to remove, right?
No, both the part, both else part.
So
I
both are.
just write return not found. That's it.
So in that case, return not found falls within the if statement
For the
itself.
outer, if I write
Yeah.
return not found. For inner, if I will not do anything.
So for the outer, if you write return not found, in that case, this return not found will be printed for every case because it is falling under the if statement only. Oh, okay, you are saying that this line 25 if
Yes,
outside, like in
yes,
this
ma'am.
same block, if I write return not found.
Yes, ma'am. Only for that. For inside, I won't do anything because ultimately we'll come
But that
outside.
statement will also be printed every time, na, if you write it outside. Because inside this definition of this function, every line has to execute. So if it is
Yeah,
outside of
that
this
is
if,
called only once, ma'am.
He's saying first indent, like
yeah, this one you're saying, na, L
Yes,
if,
ma'am.
okay. So here if I just write return not found.
Okay, ma'am. I'll just try, ma'am.
So
I'll
it
try
will
on
return, okay, I understood. You're saying that it will return the cost route inside, and if that is not the case, then it will come outside and return
Yes,
not found.
that's
Yeah,
right.
I think that will also work. First indent, you can try it. Yeah.
Okay, ma'am. I'll try, ma'am.
Okay. Any doubt in this question, anyone? Okay, you can take the screenshot of the code if you want. This part these are visible. I think the suffix is not given, but the prefix will be visible. This add all path. Okay. So next week, both revision sessions are there. No coding session will be there. Again, from the week after that, we will resume with week 6.
Ma'am,
Yeah.
can we access these codes?
These codes, I don't know if you can access. I mean, this is in my portal, right? You won't be able to access it.
I mean, can you post it in Discord?
I can post it. Yeah. Just do one thing. You just make a post and ask me for it, so I don't forget. I will post the codes.
Okay.
All right. Yeah. Okay, that's it from my side, everyone. Thanks for joining.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Yeah. Thanks.
Hello.
Yes.
Ma'am, when will the PYQ sessions start?
PYQs, I think in the revision sessions next week.